All right, we're getting very close to being able to do problems using the rotational version of Newton's second law. Rotational Newton's second law looks like this. If you add up all the moments of all the forces, so that's the net moment about the axis A, or the point A in 2D, that's equal to the mass moment of inertia about that same axis A times the angular acceleration. There are some restrictions on what can be used as the axis. A has to be either fixed in our coordinate system or the center of mass of the body. Well, we're always going to do things that we're always going to do problems where the axis of rotation is fixed in the coordinate system. So this is for later classes. And in this class, this is the definition. And what I want you to really concentrate on, this is the moment of the force. This is what we're going to talk about today. That's the load that causes the rotation. And you can think about all this stuff exactly as analogs to Newton's second law. So just like this causes the rotation of an object, in regular Newton's second law, the force, the net force, or all the individual forces added together, are what cause the acceleration of a body. On the other side of the equation, in both Newton's second law and this rotational version of Newton's second law, we have this measure of the inertia of a body. It's in regular Newton's second law, that's the mass, and in rotational Newton's second law, that's the mass moment of inertia. And that tells you how much the body itself resists having a rotation started or stopped. How much it resists changes in rotational speed. So this is a measure of the body's resistance to rotation. And I want you to think of that as just the rotational version of mass. It's not the same thing as mass, you measure it differently, but it resists changes in rotation the same way that in Newton's second law, the mass is a resistance of the body to changes in velocity. And then this is the angular acceleration. Just like in Newton's second law, that's the place for the acceleration. So we have the thing that causes the motion is equal to the body's resistance to the motion times whatever the form of acceleration in both of these two equations. So it makes it really easy to remember this if you think of it in terms of the analogy with Newton's second law. Well, we've defined the mass moment of inertia, so we still need to define the moment of a force. And so that's what we're going to do today. Okay, well, eventually you're going to see in later classes that the moment is really a vector. But in this class, since we're doing everything in 2D, we're just going to think about it as a scalar. And so first I want to give you sort of an intuitive meaning of the moment of a force. Okay, so let's say that you're trying to cause a rotation of this bolt, and you're trying to cause that rotation by applying a force to this wrench. Okay, and say that you're excuse me. Let's say that you're capable of applying a force of 100 newtons to this wrench. Where would you be most likely to get this bolt to turn, or where could you get this bolt to turn the fastest to change its angular velocity from 0 to something the fastest? So think about the center of this bolt as being the axis that we're trying to rotate it about. That axis goes into and out of the page. In 2D, you can also just think of it as a point that we're trying to cause this rotation about. And think about applying your 100 newtons of force in a couple of different places. So think about applying it here, or here. And one more, think about applying it at the end again, but this time applying it horizontally. Where would you get this bolt to rotate the most effectively? Well, you know from experience that the 100 Newton force that's way at the end of this wrench is going to make it turn more effectively than applying that 100 newtons of force close to the close to the bolt. So there's something important about the distance from the axis to where you're applying the force. Okay, there's something important about that. But now think about what would happen if you applied that horizontal force. You're still applying it far from that point. But that wouldn't rotate this bolt at all. And so the direction comes into it somehow too. Okay. And so it turns out that what matters is the distance from the line of action of the force to the axis. So let's say that the line of action of this force is this, okay? Then the distance from the axis to that line of action is, d in this case, okay? Let me get rid of that stuff. What about the one that we know intuitively is going to work the best? Well, the line of action of this force the distance from the axis to that line of action is this d, which is much bigger. And the fact that that d is so much bigger is why you get a more effective rotation from this 100 Newton force than the one that's closer to the axis. What about the third one? Because that force is being applied still just as far from the axis, but that wouldn't cause any rotation at all. So why is that? Well, the line of action of this force, if you just extend that vector in both directions, goes right through the axis. And so the distance from the line of action to the axis is 0 in that case. Okay? And so the moment of the force, the moment produced by this 100 Newton force, is plus or minus the magnitude of the force times d, where d is the distance from the force's line of action to the axis A. Okay. We also need to know the sign, and so the sign of this moment is positive if the force would cause a counterclockwise rotation about that axis. And the sign is negative if the force would cause a clockwise rotation about that axis A. So in this case, let's think about it, and let's think about the one that would produce the biggest moment. Okay. Well, if this thing is capable of moving around a hinge at A, and imagine that there, in real life, there might be a lot of other forces going on, including friction and whatever, but we're going to imagine that this 100 Newton force is the only force being applied to this body. Would that 100 Newton force make it rotate clockwise or counterclockwise? In this case, if you applied the force there, it would make that bolt rotate counterclockwise. And so that says that the sign of that moment produced by that 100 Newton force is positive. So the total moment would be 100 times whatever that distance d is, positive. Okay? So that's how we're going to calculate moments. And by the way, the sign of moments, sorry, not the sign, the units of the moment are units of force times units of length. And so that says that the SI units are Newton meters. Now, we've seen units of Newton meters before. And in the past, when we've used that, it's been to represent energy. And we gave that its own name of joules. When you're talking about moments, we're not going to, even though that is units of joules, we're not going to call it joules, because even though moments and energy have the same units, you can't add them. They're not the same thing. They mean different things. And so we don't want to get them mixed up. So don't call this joules. Okay. Let's do an example. So let's say that we have a rectangular body. And let's say the length this way is 3 meters. And the length this way is 1 meter. And let's say that the axis is here. Okay. And let's say that a force of 100 newtons is applied like this. Okay. And we want to know what's the moment applied by that 100 Newton force. Okay, well, what we're going to do is we're going to imagine extending the line of action of this 100 Newton force. So there's the line of action. And now we want to calculate the shortest distance from that line of action to the axis. The force is 100. And remember, we're going to have to think about the sign in a second. And the shortest distance, the distance from that axis A to the line of action is 1 meter. And now we have to think, if you applied that force and there was nothing else preventing this rotation from happening, would that force make this rotate clockwise or counterclockwise? In this case, it would make it rotate counterclockwise. So we know the sign of this moment is positive. And so we get a moment of positive 100 Newton meters. Okay, let's do one more calculation because if you look back at the rotational version of Newton's second law, we didn't just have single forces, we had net forces. So let's do one where we have a body and there are several forces applied to it, and we want to calculate the net moment. Okay, well, let's say we have a body. Think of this as like a seesaw. Okay, let's say this distance is 2 meters. This distance is 3 meters. And let's say that we have a force at this end of, let's say, 400 newtons, and a force over here of 200 newtons. What's the net moment acting on this body? What we have to use as our axis is the point on that body that's fixed to the ground, fixed in our coordinate system. And so this has to be our A. That's the only point on this body that never moves in our coordinate system. Okay, so that means we're going to calculate the moments of these two forces about that axis A. Let's do the 400 Newton force first. So think about extending its line of action. And then the distance that we want is the distance from A to the line of action of that force. So our MA is plus or minus the force of 400 times the distance from the axis to the line of action of that force, which is 2 meters. That force, if it was the only thing acting on that hinge, only thing acting on this body, it would cause a counterclockwise rotation around that hinge. You see that? And so that means that this moment is positive. And so we have a moment of positive 800 Newton meters caused by that 400 Newton force. And now we'll go to this 200 Newton force. So extend the line of action of that force. What's the distance from the axis to that line of action? In this case, it's 3 meters. So we have our force of, plus or minus, our force of 200 times our distance from the axis to the line of action of 3. And now think about the direction of rotation that would be caused by this force if you got rid of the other stuff. That force would make it rotate clockwise. So in this case, we're going to have a negative moment. And so if you calculate this, you get a value of negative 600 Newton meters. Now that we've dealt with the moments for each individual force, we can calculate the net moment about that axis. And you just get it by adding up these values. So 800 minus 600 gives you a total value of positive 200 Newton meters. And since it's positive, and since now we've calculated, added up the moments from every force acting on this body, that means that, that positive says that these forces all together will combine to cause a counterclockwise rotation of this body. Okay, so the load that we're applying that's going to cause a rotation is going to cause a counterclockwise rotation, and the magnitude is 200. Okay, so how much is that 200 Newton meters going to make it rotate? Is it going to make it have a huge angular acceleration or a tiny angular acceleration? Well, that we can't figure out just from the moment of the forces on its own. That's where we have to go to the rotational version of Newton's second law, and we have to include the mass moment of inertia. So if this thing has a very big mass and and that would lead to a very big mass moment of inertia, then the angular acceleration caused by these forces wouldn't be very big. If this has a small mass, and that would lead it to have a small mass moment of inertia, then these forces would combine to produce a very large counterclockwise angular acceleration. So that's moment of a force about a point. And tomorrow we'll put it all together and into the rotational version of Newton's second law.